Hi everybody and welcome to Six Sigma and Processi Produttivi YouTube video channel. This is my second video in Italian and this video is about the normal distribution, as you can see from the introduction slide that we can see now. The normal distribution is a topic that represents the basis of our webinar, because if we know the normal distribution theory and statistical meaning, we have the basis to understand all of the upcoming Six Sigma tools that I'm going to explain and present in the next tutorials. The normal distribution is also said the Gaussian curve or the bell-shaped curve. This is the pictorial representation of the Gaussian curve, and here you can see a bell, and the reason for which there is a picture of a bell is to immediately realize that the shape, the profile of the Gaussian curve immediately reminds the shape, the profile of a bell, and that's the reason why it is called also the bell-shaped curve. But let's go to the statistical meaning of the normal distribution. We see here again the picture of the Gaussian curve, but if we represent the Gaussian curve in the context of a Cartesian axis and we put on the y-axis the frequency, that means how often a value is obtained in a set of measurements, and we put in the x-axis the value of a measurable variable, variable that can be a length expressed in millimeters, a value of energy expressed in joule, a value of force expressed in Newton. You can get data that will form the profile of a normal distribution. How to get this data? If you look at this chart was presented also in my introduction video, and here are represented 10 values, 10 samples. Each sample is a round-shaped part, for example, coming from an injection molding process. Each round-shaped part is measured. We measure the external diameter of each round-shaped part so that we get 10 values of external diameters. These are the 10 values of external diameter expressed in millimeters. And there is a value of external diameter per each sample, and this way we get 10 values. Let's try to put these values in the context of the Cartesian axis to get the normal distribution, a Gaussian curve. So if we get the first value, which is a value in millimeters of 63.4, we place this cross on the x-axis. Then we get the second value, which is 63.2, and we get the second value on the x-axis, which is lower than the previous one, because 63.2 is less than 63.4. Then we get the third value, which is 63.0, and we get we place a cross here, and this value is lower than the previous two obtained. But if we get the fourth value, 63.2, 2, we immediately realize that we get the same value before, because these two values are equal. That's why we place a second cross, okay, exactly in correspondence of the value of 63.2. And you can see that we have on this line an increasing number of crosses. Here we have two crosses, while here we have only one cross in correspondence of just one single value of 63.0, and here we have one cross just in corresponding of the single value of 63.4. Here we have obtained twice 63.2, so we have two crosses. And if we get additional values of 63.2, this line will increase in height, because this line represents the value on the y-axis, so the frequency that ultimately means how many times this value has been obtained in a set of measurements. Let's try then to build a Gaussian curve with a practical example. On the x-axis, as we said, we need to have values of a measurable variable. A very common and easy example could be the number of M&Ms in a standard bag. If you think that there is always the same number of M&Ms in a standard bag, you're wrong. Typically, there are 28 M&Ms in a standard bag, but let's take 20 bags of M&Ms. Open the bags but don't eat the M&Ms, and start to count. Once we have finished to count, our counts would have probably led to something like this. 6 bags with 28 M&Ms, 5 bags with 27 M&Ms, 4 bags with 29 M&Ms, and then the remaining one. 2 bags with 26 M&Ms, 2 bags with 30 M&Ms, and 1 bag with 25 M&Ms. This way we have obtained the values of the measurable variable for the x-axis, which is exactly the number of M&Ms in each bag. So we have obtained 28, 27, 29, 26. These values will reside on the x-axis of the Gaussian curve, while in parallel we have obtained also the relative data for the y-axis. So, as we said before, what resides on the y-axis? The frequency. What is the frequency? How many times the value of the measurable variable has been obtained. So, in this case, the value of the measurable variable is 28, because the measurable variable is in this case the number of M&Ms in a bag. So 28 has been obtained 6 times, because 6 bags were containing 28 M&Ms. So 6 is for the y-axis. 27 was the number of M&Ms obtained in 5 bags, so 5 times. So 5 is for the y-axis, and in the same way 4 is the value for the y-axis in correspondence of 29 M&Ms. Let's then fill up x and y axis with the obtained values. So here we have the y-axis that represents the frequency of a given value. Here we have the values of the measurable variable that, as we already said, is the number of M&Ms in each bag. And the 6 values obtained are 25, 26, 27, 28, 29, 30. But how many times each value has been obtained? We already know that the value of 28 has been obtained 6 times. And so we put 6 crosses, okay, in correspondence of the value of 28. How many times we have obtained 27 M&Ms? 5 times, because there were 5 bags with 27 M&Ms, and here we have this line of 5 crosses in correspondence of the value of 27. How many times we got 29 M&Ms? 4 times, because there were 4 bags containing 29 M&Ms, and so we have here a line of 4 crosses in corresponding of 29, which is the value of M&Ms. And completing the distribution of data, we have 2 values, 2 occurrences, 2 frequencies in correspondence of 30, 2 occurrences in correspondence of 26, and 1 occurrence in correspondence of 25. Well, we have obtained this array of data, this distribution of crosses. If we try to draw the profile of this distribution of data with this yellow pen, we get a profile like this. And if we look at this profile, which is, let's say, roughly drawn, we see that this yellow profile immediately reminds the normal distribution. Immediately reminds the Gaussian curve. It immediately reminds the bell-shaped curve. Well, let's make some more considerations about the Gaussian curve. Value with a high frequency. Values with a high frequency, like the 28 that occurred 6 times, because there were 6 bags with 28 M&Ms, so it is a high frequency, reside in the central portion of the Gaussian curve. This portion of the curve is high. You can see that this is the central portion of the Gaussian curve, and in this portion the Gaussian curve is very high. So values with a high frequency in the central portion of the curve, while values with a low frequency, like the 26, because there were only 2 bags with 26 M&Ms, and the values like 30, because there were only 2 bags with 30 M&Ms. So values with a low frequency reside on the tails. These are the tails of the Gaussian curve, and the tails are lower in height. So we can see here that the central portion of the Gauss curve is high, while the tails of the Gauss curve are low. Some more considerations on the Gaussian curve. There are some differences between an ideal Gaussian curve, the yellow one that I tried to draft before, very roughly, and the real distribution of 20 data as a result of the counts related to 20 bags of M&Ms. The first difference is that the Gaussian curve is symmetrical, completely symmetrical, because it's a mathematical output of a formula, while the real distribution is not, while the tails of the Gaussian curve, since again it's the mathematical output of a formula, tends asymptotically to a value of 0, while the distribution doesn't behave like this. And you can immediately realize that there are these 2 differences, because here you can realize in the ideal Gaussian curve that it is completely symmetrical, while the real distribution is not, while here the 2 tails tend asymptotically to 0, while in this case there are no values of 31, 32 or 24, 23. So these tails don't tend asymptotically to 0. And final consideration is that many of everyday data set follow a normal distribution. The normal distribution is present everywhere. Everyday life data set. Many of everyday life data set follow normal distribution. Some examples are the heights of adult humans in a given geographic area. If you take, for example, 100 people in the north of Italy, and you measure the height of each person, and you plot the data on a set of Cartesian axes, you will see that plotting the heights will result in a normal distribution, or in a distribution of data which reminds immediately the Gaussian curve, the bell-shaped curve. The same occurs for the diameters of round-shaped parts. We were presenting at the beginning of this presentation a chart with 10 values of the diameters, the external diameters of 10 round-shaped parts. If you plot this data on Cartesian axis, you will get a distribution of crosses that immediately reminds the bell-shaped curve, and the same as we have just seen as an example, the number of M&Ms or other sweets in a set of decks. Well, dear all, this tutorial is finished. I hope you have enjoyed it. If you have enjoyed it, please put a like in YouTube, and don't forget to subscribe and to activate the bell so that at the next tutorial, at the next presentation published, you will be notified. Thanks again for staying with me, and see you at the next tutorial. Bye bye.